All right, one last video here. This is on unsaturated flow and karst flow. This is not on any tests. I don't have any homework for you. I don't even have any exercises for you to work in these notes. I have made some notes that you can follow along or you can put in your records, but like I said, there's no exercises in there. That's just to give you a taste of these two topics that if you ever need to or want to learn more about it, you'll have a starting place for it. But basically, I'm just going to kind of show you some pictures and give you some general information. So I want to start with unsaturated flow. There is something about this in the text in chapter 14. Now, unsaturated flow, if you look at this, first of all, notice that he makes a distinction between the vadose and the unsaturated zone. I think I said previously those are synonyms, but you can see that the vadose zone he defines as going down to the water table. The unsaturated zone goes down to the capillary fringe. That's because the capillary fringe actually has water in it, but it's above the water table. It's drawn up in there by capillary forces. So the saturation is the fraction of the pore space filled with water. So the volume of water, the volume of voids. So if you look here, the degree of saturation, you are going, it can vary across the unsaturated zone, but the capillary fringe, actually the pore space is filled with water, so it's saturated even though it's above the water table. So the hydraulic conductivity and the flow in a saturated zone are a function of the saturation. Actually, we define it relative to the moisture content, which relates to the saturation. So this cross-section showing the distribution of the water in there. So the capillary fringe is an important thing. The capillary forces are, if you have a really small straw, or this is how water goes up in trees, it'll draw water up above the water table. So the capillary fringe is that distance from the water table up that it draws the water in. Coarse sand, it might only be 2 centimeters. I think of it as a few inches, but actually in a clay or something with really small pores, it can be like 2 meters. Again, the capillary fringe is part of the saturated zone, but it has negative gauge pressure. So at the water table, it's in equilibrium with the air. So it has 0 gauge pressure. So if we have water above that, if you remember back to like the first or second video on hydraulics, we actually have a negative gauge pressure in the capillary fringe. Defining the moisture content, it can be defined relative to the solid mass or the total volume. So there's different terms for that. So the gravimetric moisture water content is the weight of the water divided by the weight of the solids. The volumetric water content is the volume of the water or the volume total. Remember, the saturation goes from 0 to 1 or from 0% to 100%. The volumetric water content goes from 0 up to the porosity. There's something called the pore water tension or metric potential. And we use the Greek letter, there's a psi for that. It's the negative pressure head. And we can actually measure that with a tensiometer. So we stick this thing in the ground. It's got a little like a ceramic thing here, and it can measure the pressure that the soil pulls on the water. So the hydraulic conductivity in the unsaturated zone is a function of the moisture content, and the metric potential is a function of the moisture content. Let me zoom out just a little bit here. So a lower metric potential means a more negative one. So they have it here. This is negative. So this is more negative as you go up. Means more pulling the water up. And if you see here low moisture content, it's more negative metric potential, and it pulls the water up. On the next page here, I show some different materials. You see the clay we have a 0.2. This particular soil, it's different soils, or particular 3 soils, I guess, at a volumetric water content of 0.2, a sand has like 10 to the minus 1 metric potential, negative. Loam is like 10 to the plus 1, and clay is 10 to the third or something like that. So it's what? more than 1,000 times higher in the clay than it is in the sand in that case. So it's a function of the material. So they have this little explanation in the text. I thought this was good. As the water infiltrates, the moisture content increases. And because the moisture content increases, it's going to the right here, then the permeability or hydraulic conductivity goes up, it increases. So then the water goes faster. So the more water you put in there, the faster it goes. And the matrix potential is changing. So its matrix potential decreases, the gradient decreases, the water infiltrates more slowly. The point of all that was it's not a simple linear relationship between the hydraulic conductivity or the matrix potential and the moisture content. You get these curves in there. And again, here is for different materials. You can fit these curves to data, or you can take data and make these curves, and there are various models to model this. Another complication of this is that, I'll zoom in a little bit again here, is that there's hysteresis. So hysteresis means it's different in different directions. So the relationship is different when the water is going in the soil than when it's coming out of it. So matrix potential is a function of moisture content, or can relate matrix potential to hydraulic conductivity. So it's pretty complex. And so I'm going to kind of leave you there after. I'm not going to work any examples or anything like that. So Darcy's law in the unsaturated zone does work, okay? Getting the hydraulic conductivity can be kind of tricky. So Darcy's law does work. One example of unsaturated flow is percolation test for like a septic field's common application of it. That typically we just measure how fast the water percolates or infiltrates into the ground. And then we put a rate on that. And actually, if we wanted to study that, take a cross section of the soil, we could have a wetting front and all that. But it's just, there's no modeling involved. We just calculate a rate. So a lot of unsaturated flow things, we just measure the infiltration into it. But there is a theory behind it. A little note here is that, actually, unsaturated flow is multi-phase flow because you have two fluids in there, right? You have air and you have water. So you're looking at the flow of water when there's another fluid in there. It's very similar if you have oil and water. So the petroleum engineers play around with this, and also in remediation, we play around with this, the movement of the water through a soil that has oil in it, or the movement of the oil in there that has water and air in it. So some similar concepts to multi-phase flow. All right, that's our one topic. And again, I'm just giving you a taste of it, kind of an introduction that if you run into it, you kind of know some things to think about. The other one is Karst. Karst Flow, and there's a little bit in our text on this, but there's another groundwater project. There's actually two other groundwater project books on Karst. I took this from Kuniansky et al., Introduction to Karst Aquifers. So the pictures I take are mostly or almost all from there. All right, so Karst Flow, we'll get ahead of things here, caves, sinkholes, fractures, stuff like that. It's not really porous media. So take everything you've learned about groundwater and never mind, throw it out. Well, not really. That's not really true, but it can be very different. So water, the things that do keep, water still flows downhill. So in Karst, again, caves, sinkholes, cracks in the rock, water still flows downhill. Potential flow and hydraulic gradient are still valid, and you can do pump tests. A karst aquifer is an aquifer. So it is groundwater, and there are big karst aquifers, like one of the biggest, the Edwards Aquifer, the Edwards Trinity Aquifer stretches. It's a big part of Texas there. It runs up in Oklahoma, Arkansas. So it's a giant aquifer that's all or mostly a karst aquifer. And the chemical transport is still the same. So you still have the same concepts as what we talked about, retardation, breakthrough curves, all that stuff still works in karst aquifers. So karst again is karst terrain, is caves, sinkholes, sinking streams. So water in the stream goes out of the stream into the rocks underneath it. Springs. It comes from a region in the Balkans where karst does, but there's karst terrain all over the world. In Texas, Pennsylvania, Arkansas, all over and all different countries. It's formed from dissolving limestones. If you look here, you have these cracks in the limestone, and the water runs through that, and as it runs through it, it dissolves out the limestone. That's how you get stalactites and stalagmites and stuff to get then it comes out in the air and it precipitates out. So it forms these solution channels as it dissolves in there. And it develops over the millennia until you get these caves and sinkholes and stuff like that. All right. Here's another picture of stuff. Again, I'm just going to kind of show you pictures, give you an idea of what it is and some places to jump off on it. So the karst terrain above the aquifer here, near the ground, we call that epikarst. Epi is top, right? Epidermis is your skin on the outside of your body. So you have runoff going in there and running in there, and then it runs down into the aquifer. And then the aquifer, I'll show another picture in a second here, the water is going through cracks and stuff, and then you can have some big kind of streams of that. When I was a kid, we had a well at our house, and they explained it was an underground river. I pictured a river down there somewhere. It's actually porous media, sand, so I learned that. Then I learned about karst. It's like, well, okay, some places there actually are rivers down there. More often smaller channels than that. And this can come out in the spring. It can go down in there. So this one, you can see, we can actually, I'm going to come back to this, put a water table on there, and then the water would come out here, and we can have a underflow karst spring, overflow karst spring, sinkholes where the water is going in, Vados conduit storage, so we have different layers. All right. So what do we still have with karst? We still have a water table. I say ish, water table-ish. I went to a conference one time on the Edwards Aquifer, and they talked about, it was really weird because after this storm, the water table went up 15 feet or something like that. So it can go up and down really fast. But still, we have unsaturated and saturated zones. We do have a hydraulic head. We can draw equipotential lines. We put in flow nets. Water still flows downhill. It does have a porosity. Now, we can see here, we have little porosity in the rocks, and then we have big porosity in the cracks, and we have bigger porosity even in the bigger cracks. So we can have different levels of porosity. It does have a hydraulic conductivity or permeability. Some special considerations in karst is the transport can be fast and far. The water levels can rise fast, like I said, and the gradient may not match surface topography. So if you look here, which this one shows the water kind of going this way. Down here, you're going uphill there, and the water is actually going downhill. So it can actually go through under a hill. It can short circuit cut under a hill. So you'll have some places, I know in the Ozarks where I hike a lot, there'd be a spring coming out of the side of a hill, and it's actually coming from a plane on the other side of the hill. And the transport can be far and fast. There was a story about a spill. I remember this in Northwest Arkansas, a gasoline spill, and like the next day, I think they had a trout pond, like a couple miles away on the other side of a hill where all the fish died. I don't know if that's really true, but it's a story that could happen in karst. Another interesting application of this is that for DNAPLs, dense non-aqueous phase liquids, they head down. So a LNAPL, light non-aqueous phase liquid, like gasoline, would hit the water table and then just float there. DNAPL keep going down. So it's really bad if there's sinkholes and caves and fractures in the rock and stuff. So it can just head down there and be super hard to find and get rid of. All right, what does work in karst? Tracer tests. I put an exclamation mark there because that's more than another groundwater. You rely a lot on tracer tests. Put a tracer in, see where it comes out. You have wells. There are wells in karst aquifers, and you can trace it that way. So that's an empirical approach to do it here. Pump tests do work. See how much water you get out. See how much the aquifer draws down when you pump it out. So that stuff still works. Darcy's law still works. So in most situations here, I have this well down here. It has the of porosity there. I can take the drawdown versus distance and the flow. I can calculate all that using Darcy's law. If I get to this thing down here where I have a big channel down there, well, then maybe that's open channel flow. So these things still work, but you just have to keep in the back of your mind that you're dealing with a different situation. Geologists love this stuff. I don't know if you're a geology person, but my son is, and I've lost students to geology. They took a geology class, and they're like, man, I'm out of engineering. Geology is the coolest thing in the world. And karst is a particularly interesting thing. And we had at the University of Arkansas, we had some really the top karst people. And so some of our students got really into that. It's fascinating stuff. So that's a little introduction to unsaturated flow and karst flow. And if you ever have to deal with it, keep this in mind and go look up some information on how to deal with it. Okay.